Hey guys, welcome to the recitation in linear algebra. So I decided to, this time I won't be so ambitious, and I decided to split the recitation into two parts, two separate parts. In the first part, so this will be recitation 8, and then the second part, recitation 8.1. So in this recitation, we will solve problems involving matrices of order 2, and then this will be followed by another recitation where we will solve problems with matrices of size 3. All right, let's get started. Well, there is this also some problems from the worksheet number 3, but also I decided to do some problems from some previous Putnam exams as well. Well, some of them are on the worksheet, some others are not, but anyway. So I have in plan to solve like a couple of problems, maybe 4, 5, or maybe even 6. I don't recall exactly, but anyway. Let's get started. Let's start. And the thing is, the first problem that I have in mind is problem number 6 from the worksheet, which says the following: let A be a matrix with real entries such that the determinant of A is -1. Now we're asked to show that the determinant of A squared plus the identity is greater or equal than 4. And well, we would like to see when that 4 is attained. So when we do have the equality case. When you look at this problem, well, there are plenty of ways to solve it. You can directly use the spectral theorem if you want. So you can say that if I have the lambda1 and lambda2 are the eigenvalues of A, then A squared will have the eigenvalues lambda1 squared and lambda2 squared, and then you know how to express the determinant of A squared plus the identity in terms of the eigenvalues, and you keep going. It's just algebra, basic algebra at the end of the day. So we can do that, or we can, let's use it without making use of the spectral theorem. Let's just write a characteristic polynomial. So the characteristic polynomial of A, of the matrix A, is given by, well, PA of lambda. This is nothing else than just lambda times the identity minus A, or if you want, this will also be equal with this guy, determinant of A minus lambda times the identity, right? You take out the -1, and you, since we have a matrix of size 2, so it will be -1 squared, so it will give you 1. So in this case, it will be the same as the determinant of A minus lambda times the identity. Okay. All right. And we know that f of 0, p a of 0, so we know that pa of 0, right? If we plug in lambda to be 0, it's nothing else than just the determinant of A, which is -1. So we know this. And now we would like to express that quantity, determinant of A squared plus the identity. So moreover, we can write, moreover, we have that the determinant of A squared plus the identity, this can be, so we can decompose that in the following ways. It's the determinant of A plus I times the identity times A minus I times the identity, which is, we know that the determinant is multiplicative, so this would be A plus I times the identity times the determinant of A minus I times the identity. All right. So we have this, right? It's quite clear. And this is nothing else than just PA of I times PA of negative I. All right, so we know this. But on the other hand, we know the characteristic polynomial is a quadratic polynomial, so we know exactly how to write it. So on the other hand, we know that that PA of lambda is nothing else than just lambda squared minus minus trace of A times lambda plus the determinant of A, right? So we know this. And we know that the PA of 0, which is the determinant of A, is -1. All right, let's see who is this guy, PA. So this implies that PA evaluated at I, so that I is the imaginary number, I squared is -1 times PA evaluated negative I, is nothing else than just, let's write it here, it's I squared minus trace of A times I plus the determinant of A times negative I squared plus trace of A times I plus the determinant of A. And we have to show that the product of this eventually will be greater or equal than 4. But anyway, let's do the computations here. So this would be equal to, so that would be, this is -1 minus trace of A times I plus the determinant of A times -1, this is the same, plus trace of A times I plus the determinant of A. All right, and now let's do the computations here. Oh my, that's not my cup of tea. But anyway, let's do it. So it will be 1 minus trace of A times I minus the determinant of A plus trace of A minus trace squared of A minus trace of A times the determinant of A. Okay. Oh my goodness, I think I forgot an I here. All right, shoot. Okay, so the first one is, so it's 1. So minus trace of A minus the determinant of, okay. The second one is plus trace of A times I. Okay. Minus trace of A, trace squared of A times I squared minus I times trace of A times the determinant of A. All right, and now the last term, it will be minus determinant of A plus trace of A, determinant of A times I plus the determinant of square root of A. All right, let's see now what will go. Oh, okay, let's do more computations. So this would be 1 minus trace of A times I minus determinant of A plus trace of A times I minus this guy here, I squared is -1 plus trace squared of A, minus I times trace of A times determinant of A. Minus determinant of A plus I times trace of A determinant of A plus determinant squared of A. Anyway, we know what the determinant is, but then now let's get rid of some terms here, and we can actually get rid of some of them. Look at this guy and this guy. This guy and this guy will just go away. And now let's see, what do we have here? So we have that. We'll also have the trace. We'll also have the determinant. All right, let's see. The determinant is, this is -1 squared. This is -1. Wow, this is -1 here. So we have 1 plus 1 plus 1 plus 1. So it will be 4 plus trace squared of A, which will be greater or equal than 4. Because this is great, so this is the square, so it's a non-negative real number, which is well, which will give us the inequality that we needed to prove. When the equality holds true, well, when the trace of square root of A is 0, which means that the trace of A will be 0. So there are infinitely many matrices for which we have equality. All right, so that was the first problem. Well, it was a bit different. It's an easy problem, but you need to be careful with the computations and stuff. Anyway, like I said at the beginning, you could have proceeded easier, in an easier way. You can, by using the spectral theorem. But if you don't know the spectral theorem, but you know what the characteristic polynomial is and what are the eigenvalues, and for example, you know this, how to express the characteristic polynomial in this form. So clearly here, you can say that the degree of the characteristic polynomial of A is less or equal than 2. So if you know how to write this, then at the end of the day, it's just a computation. Okay. So that was problem number 6 from the list. Now let's see what else do we have here. Okay, now, in fact, let me do another one, which is similar with this one. Well, I wouldn't say that's similar. And then, so problem, I'm not going to put any number here. So some, I don't know, Romanian math Olympiad, God knows what year, I don't know, in the 90s. I usually put this problem, I think, in a mock Putnam exam when I was at Pitt. I remember doing this. So it's a very nice problem. I remember it, which says the following. Let me consider two matrices, A, B, and M2 of C, such that these two matrices commute. AB is the same as BA. And moreover, we have the following. The determinant of A plus B is the same as the determinant of A plus 2B, is the same as the determinant of A plus 3B, right? And moreover, they're equal to 1. Show that B squared is the null matrix. I want you to look at it. You see, remember, this rings a bell. I think we did a problem in the lecture, and I did in the first lecture. I did a similar problem, which was given at the Putnam. I think it was that Putnam B4 in 1990. A4 1991. I don't remember anyway. I forgot the year. Remember when we had those matrices? We had a matrix 2A, B. There are two matrices with an M2 of Z. So the entries were integers, and a plus b, a plus 2b, all the way to a plus 5b, all of them are integers, have integer entries, and moreover, their inverses are in M2 of z. Show that a plus 5b is also the same way. So remember when we, well, it's kind of similar to that. So the way we're going to do it is the following. Let's consider the following polynomial function, well, the quadratic function. So consider the PAB, almost like the characteristic polynomial of lambda. This is the determinant of A plus lambda B. And we have proven that well, I didn't prove it, but I actually told you how to prove it in the lecture. So that this guy will look like this. So this is, okay, let me write it in this way. So we have seen in lecture 8 that PAB of lambda is equal to, so let me write it again. So the determinant of A plus lambda B. We have seen that actually we can write this in the following way. The determinant of B times lambda squared. And now I'm going to have a plus. I'm going to have this quantity here, very important quantity, trace of A times trace of B minus trace of AB times lambda. And the free coefficient will be nothing else than just plus the determinant of A. So we have this way of writing it. All right, what do we know? We know from the hypothesis, so we know that PAB of 1 is the same as PAB of 2 is the same as PAB of 3, and moreover, they're 1. So we know that for three distinct values, that the polynomial is constant. And keep in mind, that the degree of this guy is less or equal than 2. So by the pigeonhole principle, it follows that, so by the pigeonhole principle, it follows that this polynomial is in fact 1, so it's identical 1. So PAB of lambda is 1 for all lambda in C. All right, so we have this. Okay. So this implies that in particular for P0 of 1, so in particular, we have that the determinant of A is 1, right? P of 0. Okay, so we have this information. All right, so we know that also the determinant of A is 1. And now we would like to see how we can deduce B squared equals the identity. So maybe this would ring a bell. Well, if we prove that the determinant of B is 0, if the trace of B is 0, then by Cayley-Hamilton, we're done, right? So this is what we have in mind. So far, we don't have any information about B, but maybe we can. There is one condition that we haven't used, and look at this guy here. The fact that these two commute, we haven't used this yet. So we would like to use that. So far, we only have information about the determinant of A. So the determinant of A is 1. All right. But can we do even more? Well, maybe we can say something about the determinant of B. Does this imply something about the determinant of B? Well, let's see. So we know that let's see, what do we know? We know that PAB of lambda is 1. But in fact, let me be direct here. Of 1 is 1, but this is nothing else than just the determinant of, because it's the determinant of A plus B, right? But also, and we know that it's given, PAB of 1 is also the same as well, we have the determinant of B plus this coefficient here. Trace of A times trace of B minus trace of AB plus the determinant of A. This guy is also 1. But okay. All right. So we know that this is also 1. But we know that the determinant of A is 1. This guy is 1. So it follows that that the determinant of B plus this quantity, trace of A, trace of B, minus trace of AB is 0. Okay. All right. Well, in fact, well, it was obvious that the determinant is 0. Well, this is actually 0. Well, since this is a constant, so the determinant, since it's the coefficient of lambda squared, then it is 0. So we have that trace of A times trace of B is the same as trace of AB. Okay, so we have this information. So now we know that let's look at some information. So we know that the determinant of A is 1, the determinant of B is 0, which is great, and we know also that the trace of A times the trace of B is the same as the trace of AB. And now we would like to prove this. What we're going to do is the following. So we know that from Cayley-Hamilton. So let's apply Cayley-Hamilton for both matrices. So by Cayley-Hamilton, applied to both A and B will give us, keep in mind that we want to obtain any information about B squared. So we need to come up with something related to Cayley-Hamilton. That's impossible not to. So apply this, we'll have, so let's see, A squared minus trace of A times A plus the determinant of A times the identity. This is O2. And also, we had that B squared minus trace of B times B plus the determinant of B times the identity is O2. And now let's see what this is equivalent to. We know that in fact, we know that the determinant of A is 1. So keep in mind that this guy is 1. And also keep in mind that this guy is determinant of B is 0. So we can translate this. So we can, and so far keep in mind that we haven't used the fact that A and B commute, not yet. So we would like to do that. So let's rewrite this. So this guy is A squared, which is, let's say we can write this as, how should I write it? Some alpha. So let me write the trace of A to be alpha. So it's alpha times A minus the identity. And from here, B squared is nothing else than just beta times the identity, right? And this will be 0, where alpha is trace of A and beta is trace of B. Okay. Now, what I'm going to do is the following. Since AB is the same as BA, it follows that, so now we're going to use the fact that these two commute, it follows that AB squared is the same as A squared times B squared, right? Okay, and now finally we apply by applying, so now it's a good idea to apply Cayley-Hamilton to the matrix AB. It follows that, let's write it, AB squared minus trace of AB times AB plus the determinant of AB times the identity is 0, 2. But now we know one thing about this guy. So this will be what? This guy is A squared B squared. And we know what this is. Okay. So we have that, we know that AB squared is A squared B squared. And also we know that trace of AB is the same as trace of A. So also these guy here, so this is this, and this guy here is trace of A times trace of B times AB plus, and this guy, we know that the determinant is multiplicative, so this is determinant of A times determinant of B times the identity. This is the null matrix. And now let's rewrite this finally. So this guy here will be equivalent with A squared B squared minus alpha beta times AB. And one of these two guys, I think it was the determinant of B was 0. So this guy was 0, so everything will be just, so this will be 0, 2. So finally, this is equivalent with A squared B squared is the same as alpha beta times AB. All right. And now we can, we know who alpha squared is, so we can just write it. You see, we have this equality is obtained here. A squared, we know who this is. We know B squared, who this is. And there is no way we cannot get something. And we know also this guy here. So let's put everything together. But we know that A squared was, let's see, alpha times A minus the identity, and B squared was, in fact, was beta times B times B. All right, let's plug it in. So we have that. Let's see, what do we have? Alpha times I minus the identity times beta B is nothing other than just alpha beta times AB. Okay, which is equivalent, if we do some computations here, with alpha beta AB minus beta B equals alpha beta AB. And from here, this implies that beta times B is O2. So we have two cases here. If beta is 0, then this implies that the trace of B is 0. And since the determinant of B is 0, by Cayley-Hamilton, this implies that it follows that B squared is 0, is O2. Well, if the other option is, so keep in mind that we're looking at this guy here, this equality here we're looking. Now, if the matrix B is the null matrix, then clearly B squared is O2. So in either case, in either case, the conclusion follows. Okay. So that's the problem. It was a nice problem. You can also, well, the official solution, anyway, it was trickier than this. It was something like you consider the matrix A, B inverse. So you prove that the inverse, or A inverse B, sorry. And then you play around with this. So you factor it, and then you consider the same polynomial. Anyway, it was trickier than this. I'm not getting into that. I don't want to lose more time with this. So you can try it. So the main idea is to look at this matrix, A inverse times B, and try to consider a similar polynomial, but for this matrix. So you consider the polynomial determinant of A, B inverse plus lambda times the identity, something like this, and try to figure out something in terms of the determinant of A plus B, determinant of A plus 2B, and so on. Okay. Now, another problem from the list was the following. Let me look at it. From the worksheet, it says the following. It was problem 8. It's a very interesting problem. And I'm going to show you a very nice solution. But anyway, let's see the statement for any square matrix A. Right? We define the sine of them of A by the usual power series sine of A is nothing else than just the sum of -1 to the power n over 2n plus 1 factorial times a to the power 2n plus 1. So we define the power series, the Taylor series for sine of A in the same way as we define for sine of x, right? And now the problem asks us to prove or disprove the following. There exists a 2 by 2 matrix A with real entries M2 of R such that sine of A is nothing else than just this matrix 1, 1, 1996 is 0 and 1. All right, so this was a Putnam B4 in 1996. It wasn't like the easiest problem. Okay, look at it. Yeah, that's the statement. Anyway. Well, you know, the usual solutions, you just have to compute the powers of, you want to see if they match up with everything there. But anyway, there is something, it's a very nice trick here that I want to show you. So the trick is the following. Well, look, first of all, let's see the question. It says prove or disprove. Well, we will disprove. We will show that, so we will show that there is no such matrix A. So that's what we're going to show. So there is no such matrix, there is no 2 by 2 matrix A such that sine of A is that matrix. As you can see, this matrix here, if we want to look at it, if we want to look closely, it will have these ones here, right, on the main diagonal. So maybe you can write it in terms of the identity. So that could be something to see, to look at. And now, let me show you a magic trick. Well, you know that the power series for, now, let us consider the following power series of the cosine. So consider the power series of cosine of A given by, and will be similar. So here we have the odd powers, so the cosine will have the even power. So this would be nothing else, a sum from n equals 0 to infinity of -1 to the power n over 2n factorial times a to the power 2n, right? All right, great. But then guess what? By the most famous, let's say, trigonometric identity, and what I mean by that is that sine squared of x plus cosine squared of x equals 1. Well, we have that. So instead of writing these functions, we can write their power series. So we have that, and let's write it in this way. So this would be the power series of sine. So we squared this guy plus, and now we write this of the cosine. And we square this, so we can write this as equal to 1. So by this famous trigonometric identity, right, the trigonometric form of Pythagoras theorem, we can substitute x equals a. But we can substitute x to be a. And we derive, let's say, that let's say sine squared of a plus cosine squared of a equals the identity in our case. All right, but let's look. We know that sine squared of a, look, it's the identity there. And if we square this, but we have that the identity, right, minus this matrix squared, 19096 01. So this guy, right, squared is nothing else than just this guy. So if we square this, this will give us 0. So this will be 1,092. So 3,992, 0 and 0. And we have to show that, well, we know that. So this is a square of a matrix. Is the square of a matrix. So we know this by our assumption. Right here, I said that we should prove that there is no such matrix. I should have written, well, suppose that there is. So we know, suppose that there exists a matrix such that sine of a is equal to that, and then we square it. And then you know that sine squared of x of a plus cosine squared of a is the identity. So it will follow that at the end that this matrix is the square of a matrix. So that's what we know. That this guy here is the square of a matrix. All right. So let's just say that. So let's say that this guy, this 2 by 2 matrix here, 0, 3,092, 0, 0, is the square of a matrix. Let's say, well, it's cosine square, but let's just say this is the square of this matrix, right? With y in M2 of R. All right, no problem. Now let's raise this matrix to the power squared. So squaring this, so clearly this guy, if you do the computations here, and I'll leave it to you, this guy here squared, it will give you the 0 matrix, right? It's just, I'll leave it to you as an exercise. So now this implies that y to the 4th is O2. But now, by using, remember we did this problem, if I have a matrix which is nilpotent, then y to the y squared is the null matrix, right? So we use this. So we used, I don't know what problem it was, problem 1, I think, in lecture 8, something like this, right? We said that if there exists k such that a matrix to the power k is the null matrix, then a to the squared is the null matrix, if provided that the matrix is a 2x2 matrix, right? With real complex entries, it doesn't really matter. And we use repeatedly, we employed the Cayley-Hamilton relation, right? And it was just an inductive procedure. All right, so we will have that y squared equals 02. Well, but guess what? So this guy is actually 02. Well, not quite, which is false. We got a contradiction, so there is no such matrix such that sine of A is that 1, 1996, 0, and 1. Well, it was a very easy problem, I would say. Well, provided that you come up with this trick by considering the power series of the cosine of A, since you have the cosine, and we know that since sine squared of x plus cosine squared of x is 1, you can consider the matrix analog of this. But anyway, okay. All right. This was problem 8 in the list. Let me do another one. Where is it? Okay. There's another problem. Problem 16 in the list. Right? Which says the following. For n greater or equal than 1, let dn be the greatest common divisor of the entries of this matrix, a to the power n minus the identity, well, where this matrix A is actually given in an explicit form. So this is 3, 2, 4, 3. And now we would like to show that this sequence of the sequence Dn has limit infinity at infinity. So the limit as n approaches infinity of Dn is infinity. And this was a Putnam, what was it? This was a Putnam. Oh my, I don't see it here. Anyway, it was a Putnam B4 in 1994, I think. Yeah. All right. Again, this is not the hard problem, it's an easy problem as well. In fact, we can even probably compute explicitly, but we don't have to write it explicitly. Yeah, so let me just tell you the main steps. By an induction, and I'll leave this to you, so by an easy induction, one can show that there exist two sequences, that there are two sequences, let's say of positive integers. Let's just say that an and bn, right? There exist these two sequences such that we can actually compute a to the power n, and it will look like, well, it's not hard to see. If you look at the way it's defined, so as you can see, the elements on the main diagonal, they're the same, right? And this guy here is kind of related to this guy here. So 4 is a double of 2. So we can imagine that this will look like, let's say, a sequence an, bn. Again, we'll have here an, and this will be 2 times bn. It's a very easy induction. So you assume this, then you write a to the power n plus 1, which will look like this, and then you multiply a to the power n plus 1 is a to the n times a. You multiply them, and then you will get a recursion. So it's a very easy, and I will leave it to you as an exercise. Well, but basically I just told you. Okay. All right, but we're interested with what happens with an. Keep in mind that we're interested in this guy, a to the power n minus the identity. But anyway, let's make some observations here. There is one thing here. You see, we know that, so since if we take the determinant, we know that since the determinant of a to the power n is 1, right? It follows that well, that an squared minus 1 is 2bn squared, right? So we have this. Well, in other words, if you if you decompose, if you factor an squared minus 1 as an minus 1 times an plus 1, so this implies that an minus 1 divides 2bn squared. Okay. So now by the definition, we know that let dn to be the JCD of a sub an minus 1 and bn. So now this implies that if we look at 2dn squared, this guy will be nothing else than just the JCD of 2 times an minus 1 squared, right? And 2bn squared. But this guy here is greater or equal, it's obvious, than an minus 1. And now from the fact that an plus 1 is the same as an times a, right? It follows that, and I'll leave it to you as an exercise to figure it out. A sub n plus 1 is greater than 3 times a sub n for all n. Again, I'll leave this to you as an exercise to figure this one out. Okay. Well, from this clearly it follows that the limit of n as n approaches infinity is plus infinity. This is a very easy to see. You just divide an plus 1 over an. You multiply, you write n equals 1, n equals 2, n equals, and so on. You multiply them, they'll simplify, and then you'll have 3 times 3 squared, 3 cubed, and so on. Anyway, so finally, this gives us that the limit as n approaches infinity of Dn is positive infinity. And we're done. But anyway, again, this was a very easy problem. And now, since we're talking about powers of matrices of order 2, there is one problem that I have in mind, and I would like to do this. This was a bit difficult, but so another problem was okay, let me state it first and then I'll tell you the source. The problem says the following: let S be the set of all 2 by 2 real matrices and let's just write them. So M will look like this: A, B, C, D, whose entries A, B, C, D in that order form an arithmetic progression. Find all matrices M in S for which there is some integer k greater than 1, such that m to the power k, so we raise the matrix is in S as well. All right, so this was a Putnam B3, quite recent, I would say, 2015. That was a hard Putnam exam. I remember this pretty well. It was a hard one. All right, so how we should approach this problem? Well, we have a very important piece of information, and that is the fact that if you look here, that these entries form an arithmetic progression, and this is very important. So in fact, we can actually write the matrix. We can write the relationship between the entries of the matrix. But we would like to see, we would like to determine all matrices in S. So how do they look like? That is the question. We would like to see. Let's see. So we know that we can write all the entries. So we can write all entries of the matrix M in terms of the first one, right? So we have A, B, C, D. These are in arithmetic progression, and we can write so B will be an A plus the constant, then C will be B plus that, the same constant, and the same goes for D. D will be C plus that constant. So we can write them explicitly. So let's see. So we have this, that M, this is important. That when we raise this to the power K, this will be in So how do they look like? So we would like to see, okay, let's see. So we know how a matrix will look like. So suppose that this matrix M belongs to this set S, and that K is greater than 1, right? Such that M to the power K is also in this set S. So we would like to exploit this. Now let's see what happens. Because we said that the common difference is constant, right? So the common difference in the arithmetic progression, let's just say it like this. So is, let's say, is T, right? So this means that means that A is A, B is A plus T, C is B plus T, and D is C plus T, or T real. Right? Okay. So we know that, so M will look like this. So let's write the matrix M. So it will be A plus T, B plus T, and let's rewrite this, A plus 2T, and A plus 3T. So this is how the matrix will look like at this point. So these are the matrices. And now let's see, we said that the common difference in the arithmetic progression is T. So that's the ratio, let's say. Now let's point out a remark. If T is 0, what do we get? We get that M will look like this. So it's A, that's perfect. So all these matrices are just scalar multiples of the of one of this matrix, 1, 1, 1, 1. And if you raise to the power k, so it will be just the same matrix. So everything will be just a scalar multiple of this, right? All right, let's keep this in mind. So now we can assume that T is non-zero. And now we would like to see what happens to this. And now let's look at this matrix. So it's a 2 by 2 matrix. And we would like to see the characteristic polynomial of this matrix. So the characteristic polynomial, I want to see what happens to the eigenvalue, the characteristic polynomial of M is given by, so let's write it, so Pm of lambda, which is the determinant of lambda times the identity minus M. This guy will be nothing else by, after some computations, anyway, I'll leave them to you. Well, let's see, I think I computed here somewhere. All right, so this will be nothing else than just lambda minus, and now the coefficient will be 2a plus 3 times lambda, 2a plus 3t times lambda, and the last coefficient is minus 2t squared. Okay. So this is the characteristic polynomial, and I would like to see what happens to the discriminant of this. So, right, we would like to find the eigenvalues, and now this. So let's look at it. And maybe we can point out some observations here. So let's see, what can we say? Clearly, the degree of PM is at most 2. We can say that. What else? What can we say about the constant term of this polynomial? Well, we can say that is negative. So the constant term, this guy here, this is negative. So clearly the discriminant will be positive. So the discriminant of the characteristic equation Pm of lambda equals 0 is positive. Okay, now let's handle this. So there are 2 distinct roots. Let's just say lambda 1 and lambda 2, right? Which are non-zero, right? Let's say distinct non-zero roots. Lambda 1 and lambda 2. Okay, so we have this. And now we have these 2 eigenvalues. I know that they're distinct, they're non-zero. And now let's see let's consider, so consider V1 and V2 their corresponding eigenvectors. Okay, all right, so now let's note that. So first, let us note that m multiplied with this vector 1, -1 will give us nothing else than just negative t, right? So in other words, m is a multiple of, negative tt. So in other words, this guy is a multiple of the vector 1, 1. And now, similarly, we can say that for any matrix n, let's say, so let's consider for any matrix n in S, okay? So for any matrix n in S, we have that n times this vector of 1, -1 is a multiple, okay, let me write it directly, is a multiple of 1, 1, of this column vector 1, 1. Okay. So in particular, we say that in particular, if we raise m, since I know that m to the k is in S, m to the k times 1, -1 is a multiple of 1, 1. And let's point out the remark here. Note that this vector 1, 1 cannot be the eigenvector of m. Of m. So this cannot happen. All right. So we can write that. So since this is not true, this cannot be the eigenvector of m. So it follows that 1, 1, we can express this as a linear combination of those vectors v1 and v2 of the eigenvalue of the eigenvectors, the two eigenvectors corresponding to the eigenvalues. So this could be something like c1 times v1 plus c2 times v2. Okay, for some constants, non-zero constants, c1, c2, not zero, right? So finally, we have that, and let's be careful here, that m times this vector 1, -1, which we know that is a multiple of 1, 1, is nothing else than just, let's say, a t times c1 v1 minus t c2 v2. So m to the k multiplied by 1, -1 will be nothing else than just negative t times so this would give us negative t times c1 lambda 1 to the power k minus 1 v1, so it minus t times c2 lambda 2 to the power k minus 1 v2. Okay, so we have this. So from here, as you can see, this latest vector is a multiple of, so this guy is a multiple of C1 V1 plus C2 V2. So this implies that well, clearly lambda 1, okay, let me write it here. So this implies that lambda 1 to the power k minus 1 is the same as lambda 2 to the power k minus 1. And since they're distinct, and this implies that lambda 1 is negative lambda 2. So we have this relation between the two eigenvalues. Right? We know that, keep in mind, we have this because both of them are real, and moreover, they're distinct, right? But now let's look at the trace. The trace of M so let's look at the matrix. So the matrix will look like this. So the matrix is, look at the elements here. You see the main on. So the trace of M is 2a plus 3. So we have that. We obtain the following. All right, and now I'm going to do the following. At one hand, the trace of M is what? We said that it's 2a plus 3t. On the other hand, is the sum of the eigenvalues is lambda 1 plus lambda 2, but which is lambda 1, negative lambda 2 plus lambda 2, which is 0, right? So we have at this point, this implies that so 2a plus 3t is 0. So we have this equality, and we can actually write the matrix. So finally, we have that our matrix M, which at first looked like, how did it look like? Like A plus T, A plus 2T, and A plus 3T. So now we know that 2a plus 3t is 0, so we can write a in terms of t. And finally, this will give us, well, so a will be negative 3 over 2t, so we can factor anything. Okay, so it will be negative t over 2 times, so we can factor this, negative 3, negative 1, 1, and 3. So these are the other matrices that we're looking for. So the scalar multiples of this. So all the matrices M that have these properties, so that belong to S and such that M to the K belong to S, are the scalar multiples of this matrix 1, 1, 1, with the entries 1, right, as you can see it here. And the last one is this guy here, the scalar multiples of this matrix negative with the entries negative 3, negative 1, 1, and 3. All right, that was a very nice problem, a little bit tricky, I would say, but anyway, you have to be careful with some stuff. And now there is one, I think I have one more problem that I wanted to cover. Where is it? Okay, here it is. It's problem 9 from the worksheet. And I think I'm going to stop after this, which says the following. I have two matrices A, B, and M2 of R. Show that the determinant of A squared plus B squared is greater or equal than the determinant of AB minus BA. Right. This is a pretty classical problem, but it's tricky. Okay, I want to show an application of that identity that I gave you. So remember that so let me consider this polynomial. PAB of lambda was the determinant of A plus lambda B, which was nothing else than just the determinant of B times lambda squared, plus, you know, that coefficient alpha times lambda, but that alpha was the trace of A times trace of B minus trace of AB, plus the determinant of A. And we know from here, we deduce that identity. So let's write it as, so we will use the identity the determinant of x plus y plus the determinant of x minus y is 2 times the determinant of x plus the determinant of y. So what we're going to do, well, we want to use this identity, and now let me just give you the main idea, and maybe you can finish off the problem. Look at this thing here. I'm going to multiply this in two ways. Right? And the other way around. On the one hand, this would be a squared minus I times AB plus IBA minus I squared, so plus B squared, right? In any case, this is A squared plus B squared minus I times AB minus BA. Okay, and this guy will give you the same, by doing the same thing, it will give you A squared plus B squared plus I times AB minus BA. All right, and now what you're going to do, you're just going to apply the determinant here to both of them, and then use the identity anyway. And you know the fact that the determinant of this product here will always be non-negative because it's the conjugate of one of the other. So the determinant of A plus IB will look like a number alpha plus I beta, and the determinant of A minus B will look like alpha minus I beta. So multiplying this, it will give you the absolute value of the determinant of A minus IB in absolute value squared, which is greater or equal than 0. Anyway, that's the idea. I think I'm going to stop here. Well, I would like to thank you. And probably next week I will start talking about matrices of order n. Okay, thank you very much.